Hi everyone, today I walk you through how I solve this constrained optimization problem using the KKT method and second-order conditions. We are asked to minimize the function fxy equal to minus x squared minus y squared, subject to three inequality constraints. Here are the three inequality constraints. And before I solve this question, I'll show you a 3D picture of this four functions. The purple one, this one is the function fxy equal to minus x squared minus y squared, and this area is equality constraints. And from the picture, we can easily to see when 1 0 0 1 minus 1 0 and 0 minus 1, this 4 point, we can get the minimized valuation of the function fxy equal to minus f squared minus y squared. Okay, so to make the question more simply and briefly, we can make the question minimize the fxy to maximize the fxy equal to x squared plus y squared. This will make the question more easily, and rewrite all inequality constraints in the form of less than or equal to 0. Here are the rewrite constraints, and make them to G1, G2, and G3. And firstly, I set up the Lagrangian function, and here is the Lagrangian function. And then I applied the KKT conditions. The first condition is stationarity. The first order partial derivatives of the Lagrangian with respect to x and y are both equal to 0. And then we get these two equations. And the second one is primal feasibility, which the constraints are satisfied. And the second one is dual feasibility. We can get lambda 1, lambda 2, and lambda 3 are all larger or equal to 0. And the fourth is complementary slackness, and we can get lambda times g equal to 0. So we can get these three functions. Okay, for case 1, all constraints are binding, so we can get these three functions, and then we can solve it and get two results. Unfortunately, these two results are all fail to pass the feasibility test, so this one has no solution. And from case 2 to case 4, we will active two of the functions. So, okay, for case 2, we active G2 and G3, and then we can get these two results. The first result has no solution. And for the second one, we can get lambda 2 and lambda 3 are all bigger than 0. So this one passed the feasibility test and has no second order conditions. And then we came to case 3. This time we active G1, G3, and then we can get these two results. And same as the case 2, the first one has no solution, and the second one passed the feasibility test and has no SOC. And then we came to the case 4. Case 4, we active G1, G2, and we have two results too. And just the same, the first one has no solution, and the second one passed the feasibility test and no second order conditions. From case 5 to case 7, we just active one of the functions. From case 5, we active G3, and then we get the functions, and then we get the results. The results has passed the feasibility test, and for the second order conditions, we can get the determinant of the Hessian matrix, and this one is equal to 0, so this one has no result. For case 7, we activate G2, and then we find that there is no solution for the functions. For case 7, we activate G1, and we have three different results. For the first and second results, all pass the feasibility test, but for the determinant of the Hessian matrix, all smaller than 0. So they are all local minimizer, and for the third result, it passed the feasibility test too, but its determinant of Hessian matrix is bigger than 0. So this one is a local maximizer. So for the last case, we active none of the functions, and we get x equal to y equals to 0. And we can get the first order determinant and the second order determinant of Hessian matrix is all larger than 0. So this is a positive definite. So it's local maximizer. Okay, in conclusion, these four conditions can have the feature of local maximizer, and all of the value of fxy are equal to 1. And so, when we back to the original fxy, which one is equal to minus x squared minus y squared? Its minimum is equal to minus 1. So all of the solution are minus 1, 0, 0, 1, 0, minus 1, and 1, 0. Thank you. Here is all my solutions, and thank you for watching.